Electronics is a science that applies these tubes to the service of man, to the speeding of production, to the winning of the war. To understand how electronic tubes work, let's take a good look at one of them, one that's representative of its species. This is a diode, a typical two-element electronic tube. Let's get inside it. In fundamental operation, it resembles an ordinary single-pole switch, a switch that can connect, for instance, this battery and its motor load. One power lead comes to the anode, the other lead goes to the cathode. When this switch is open, the contacts are insulated from each other by a vacuum, or by some inert gas inserted into an evacuated tube under low pressure. To close this switch electronically, all we need do is heat the cathode and give the anode a positive potential. Then here's what happens. As electrons are emitted from the surface of the heated cathode, being negatively charged, they fly at tremendous speed to the anode. In this way, a current-carrying path is formed, which closes our electronic switch and permits our motor to operate. You'll notice, by the way, that the direction of electron flow is contrary to the orthodox concept of current flow from plus to minus. Now, at this point, you may ask, if an electronic tube is basically just a form of switch, why is electronics hailed today as the technique of a new engineering era? To answer that question, let's review 6 of the basic things that we can do with this new kind of switch. In the first place, we can rectify current with it, converting AC to DC. We can do this merely by connecting an electronic tube in series with an AC circuit. As you study this circuit diagram, note that only each positive half wave of AC voltage will now produce a current. When the anode is negative, the electrons are repelled and no current flows. In other words, because only the cathode can emit electrons, we have here what amounts to a one-way street. We can visualize the result of the tube's rectifying action with the aid of these 2 oscilloscopes. The one on the left shows alternating current coming in. The one on the right shows pulsating direct current going out. The applications of this basic rectifying principle are many and important. Here's one of them, changing AC to DC on the nation's electrified transportation systems. Here's another, rectification for electroplating operations of all kinds, operations possible only with direct current. Still another example, furnishing DC in steel mills for the driving of variable speed motors, such as the one controlling this giant ladle, or the ones driving steel conveyors with such precise control of speeds that danger of buckling and tearing and consequent mill damage is eliminated. Electronic rectification is also helping to build American air power by making available record-breaking quantities of aluminum for plane construction. From Arkansas mud to American air power involves a complicated conversion of material. Before pure aluminum can be extracted from this bauxite ore, direct current must be applied in a vital reduction process. To obtain that direct current from AC transmission lines, the ignitron rectifier is used. This Westinghouse electronic development changes vast quantities of AC to DC with higher efficiency than any similar type of conversion equipment. Today, it's the main source of current supply for the nation's great aluminum industry, an industry that has achieved a miraculous expansion to meet the demands of a world at war. Magnesium from seawater is another achievement of industry under the stress of war. Ignitrons used in the extraction process speed up the delivering of incendiary and demolition bombs to the centers of Axis production. Still another example of electronic rectification at work is the precipitron, a device for cleaning air electrostatically. This diagram explains how the precipitron works. The rectifying property of electronic tubes is used to apply a potential of 13,000 volts DC to tungsten wires and 6,500 volts DC to collector plates. As incoming air passes through the field of these wires, each particle of dirt receives a positive electrostatic charge. When the positively charged particle reaches the collector chamber, it's attracted to and deposited on negative plates. In this way, air is cleaned so thoroughly that dirt particles down to a 1/4 millionth of an inch are removed. This is a vital advantage today, not only in homes and public buildings, but in industrial plants of all kinds. For instance, in plants manufacturing delicate instruments, where air cleanliness is necessary for precision work. In workrooms where optical systems are assembled for a host of military purposes. In inspection rooms where minute parts must be closely examined under high magnification. Air cleanliness is vital, too, in film developing rooms like this one. To understand how electronic air cleaning helps here, let's go aloft in a reconnaissance plane. Click. 5,000 feet above the earth, a camera shutter opens and closes. Scores of square miles of enemy territory have been squeezed down into an image on a photographic plate. An image measured in inches instead of miles. On this photograph, a city might be covered by a tip of a finger. A speck of dust could hide a Nazi aerodrome. The rectifying tubes of the percipitron help make sure that dust doesn't sabotage military photography.